Last time, we applied the propositional calculus to the construction of formal proofs. Now, we consider informal proofs. What's the difference? For a formal proof, we're assuming Boolean logic. So every statement that we have will have a value of either true or false. In fact, you'll note in the work that we've done, we didn't worry about what the statements actually were. We're just interested in seeing what we could do, assuming true or false. A type of statement where Boolean logic wouldn't apply, okay, try this statement is false. Now, for informal proofs, it's going to be the same basic idea, except there's going to be some looseness, so we'll need to be careful. Now, what types of things do we need to watch out for? First, our everyday language is subjective. So, the words that we choose will affect the meanings of our statements, so we need to be careful. Another problem, because of language, we'll also have trouble deciding when things are true. Okay, so historically, mathematicians have had problems with the axiom of choice. Another thing we'll see in informal proofs, unlike a formal proof, we don't have to explain every step. So mathematicians, okay, don't want to keep proving things over and over again. So we hand wave those by saying, okay, the statement's clear or the statement's obvious. So when you see that, you know you have to do some work or some rechecking. One last thing, an informal proof, okay, because of the language issue, that can be very difficult to check and time consuming. Okay, on the other hand, if you want to check a formal proof, okay, because of the way Boolean logic's set up, this is the type of thing you could program into a computer, let it run, and it'll check your work. Okay, usually we can't do that here. Now, for informal proofs, we now want to go through the different methods of proof. Okay, so some of these will be familiar. First, I have direct proof. This is just going to be taking a collection of hypotheses, showing that they logically imply the conclusion that we want. So for an example, let's consider the sum of two even integers is even. Now, this looks like an obvious statement. Okay, if you take 2 plus 2, you get 4. Take 4 plus 2, you get 6, and so on. Every time you check that, it's going to work out. Problem is, checking like that is not a proof, since we'll never be able to check every case, since we don't have an infinite amount of time. Now, the way to get around that, we want to set up definitions that we can work with. So here, I'm going to assume that we know what an integer is. We're going to need a definition for even, so that we can do our bookkeeping a little bit nicer. So my definition is going to be an integer n is even if we can write n equal to 2k for some other integer k. Now, for our proof, we'll set it up like we did before, okay, just for this one. So what do? We announce that we have a proof. I'm going to start with the hypothesis. Okay, I'm going to take two even integers, we'll call them m and n, and we're going to add them together. So the first step is just to assume that m and n are even integers. Now, by our definition, we could write m equal to 2k, n equal to 2l for some integers k and l. So that's definition. We add them together. So m plus n is equal to 2k plus 2l. Okay, and here we're using statement 2. For statement 4, I'm going to factor the 2 out. So we could do that using distributive property of addition and multiplication. Then finally, okay, we go to our definition. We have 2 times an integer. Okay, k plus l will be an integer. So that means m plus n is even by definition, okay, using 4. So that's the proof of our statement. Now, some theorems don't lend themselves well to direct proof, so instead we try indirect methods. One way to do that, we use the contrapositive of the statement that our theorem is true. So this gives us proof by contradiction. What we do, we're going to negate the conclusion And then from that, we're going to try to derive a statement that we know is false. For an example, let's try the theorem. There's no rational number x such that x squared is equal to 2. Okay, in other words, square root of 2 is an irrational number. Now, if we were to try direct proof, okay, well, that would amount to checking all rational numbers, squaring them, and seeing that they're not equal to 2. So somehow we would have to come up with that argument. It's better to do this indirectly. So what we'll do, we take the negation of this statement. So that's going to be that there is a rational number such that x squared is equal to 2, and then we try to derive a contradiction. Now, we set up our proof. So we announce that we have proof by contradiction. We take our negation. Okay, so we're assuming that there's going to be some rational number x with x squared equal to 2, and then we proceed. So we would do our work off to the side, and then we write the proof up nicely. Now, if we have this rational number x, we can write in the form p over q, where p or q are integers, and they have no common factors. So we'll assume that we're in reduced form. Because of that, we have that p is equal to q times x. And if I square both sides, I get p squared equals x squared q squared. By assumption, x squared is equal to 2. So I'll have that p squared equals 2q squared. Now, that means 2 is going to divide p squared. Since 2 is a prime, that means that 2 is going to divide p. So because 2 is prime, I can't split that and put a factor into each p. It has to divide entirely into one of the p times p. So, from what we've seen before, okay, to have 2 dividing p, or having p an even number, that just means that p is equal to 2 times k for some integer k. Now, that means p squared is equal to 4k squared, but it's also equal to 2q squared. So I have q squared is equal to 2 times k squared, and that means that 2 divides q squared. As before, that means 2 divides q, and that means 2 is a common factor of both p and q, a contradiction to the fact that our rational number is in reduced form. So contradiction, that means our conclusion is true. Now, let's clean up a definition from the previous board. I'll say an integer p greater than 1 is called prime if, when an integer m divides p, so that just says that p is equal to m times k for some integer k, and we have that m is greater than 0, then m is equal to 1 or p. So if I try to factor p, the only way I can do that is as 1 times p. There's nothing in between. So numbers that are prime would be like 2, 3, 5, 7, and so on. 4 and 6 are not prime because we could factor into 2 times 2 or 2 times 3. Now, we have the following theorem of Euclid. So that says there exist infinitely many primes. If I want to try to prove this directly, I need to come up with some mechanism that generates an infinite list of primes. So we're going to want to do this indirectly. So we use proof by contradiction. So we announce proof by contradiction, and we negate our conclusion. So that'll be there exist finitely many primes. Now, because there are finitely many, I can list them. So I'll have p1 equals 2, p2 equals 3, and so on until we get to the last prime, which is p sub I. For our next step, we're going to take that finite list, multiply all the primes together, and add 1. So I'll call that number n. Now, first thing to note, n is strictly bigger than any of our primes. Okay, so if I take an integer, positive, multiply by another positive integer that's greater than 1, then add 1, that's going to be bigger than the prime that I used. Now, because n is greater than all of our primes, n itself cannot be prime. So that means one of our primes has to divide n. That means n is equal to p sub k times m for some integer m. Now, let's write out what that means. So I can write n in this form and in this form. So what I can do, I'll move this product to the other side. So we're going to have a difference. And I could factor out a piece of k out of both of these terms. So that leaves me with piece of k times this integer is equal to 1. Now, easy result to show. If I have m times n equal to 1, that means m and n are both equal to 1, or m and n are both equal to -1. Because we have a factor piece of k, which is a prime strictly bigger than 1, we arrive at a contradiction. So that shows that we have infinitely many primes. Getting back to proofs in general, we note that sometimes it'll be useful to split our proofs into cases. So here, I don't want to split our proof into several smaller proofs. For an example of this, we have the triangle inequality for real numbers. Now, to start, I'll have a definition. So if x is a real number, we'll define absolute value of x to be equal to x when x is greater than or equal to 0, or minus x if x is a negative number. So this is what you normally think of for absolute value. If you have a positive number or 0, you just return the number. If you have a negative number, you take away the minus sign, and that's the same as multiplying by -1. Now, the triangle inequality says, okay, with x and y real numbers, then the absolute value of x plus y is less than or equal to the absolute value of x plus the absolute value of y. Before we do the proof, let's talk about what this really means. Now, where does the name come from? Well, we're going to have several versions of the triangle inequality. The triangle comes in with the version in 2D, so in R2. So here, we have a notion of vectors and vector addition. If we take two vectors x and y and we add them, then the picture is going to look like a triangle. And what the triangle inequality says is that the length of this side is less than the sum of the lengths of the other two sides. Now, what does the geometry of absolute value of x look like? Well, all we're doing here for the real number x, when we take the absolute value, we're just taking the distance from 0 to x. So if x is positive, okay, we're just taking the number itself. If it's negative, we throw away the minus sign, then we're just getting a positive number back. Now, the idea here, okay, if we think in terms of measuring distances, okay, we can draw some pictures to get a feel for this. So the idea, what the triangle inequality is doing, we take two real numbers x and y, we're getting some control over how far from the origin we get with x plus y. So for an example, if we took, say, 3 and 4, so both positive, we add them together, we note that the distance from the origin when we add is going to be exactly the sum of the lengths of the distances from the origin of each. If I have a positive and a negative, okay, so here I'll take 3 and -2. We add those together, we get 1. If we add their absolute values, we get 5, and 1 is strictly less than 5. So the triangle inequality holds here. Note, okay, we have a lot of room when we do our addition. Okay, so when I have a positive and a negative, okay, we're actually eating up this space over here. Now, to proceed, we use a direct proof with cases. Here, we'll assume some identities with inequalities that are very believable. Okay, we start with proof, and we announce that we're splitting into cases. For our first case, we have x greater than or equal to 0, y greater than or equal to 0. Then, by definition of absolute value of x is equal to x, absolute value of y is equal to y. And we have that if we add x and y, we get a number that's greater than or equal to 0. So its absolute value is also equal to the number. So absolute value of x plus y equals x plus y. Now we just follow out the equalities. Absolute value of x plus y equals x plus y. x is equal to absolute value of x, y equals absolute value of y. So absolute value of x plus y equals absolute value of x plus absolute value of y. This implies the weaker statement that the absolute value of x plus y is less than or equal to absolute value of x plus the absolute value of y. So that gives us the triangle inequality in this case. Next, we assume that both x is negative and y is negative. So here I'll have absolute value of x is minus x, absolute value of y is minus y. If we take their sum, we'll have a negative number, so the absolute value of x plus y is equal to minus x plus y. Same as before, we follow out the equalities. So absolute value of x plus y equals minus x plus y, which is equal to minus x plus minus y. That's equal to absolute value of x plus absolute value of y. And as before, that implies a triangle inequality. For our final case, I have x greater than or equal to 0 and y less than 0. Now, you might think that there's a case 4, but since I haven't told you what x and y actually are, that fourth case is just going to be the same as case 3. So that would be y greater than or equal to 0 and x less than 0. Now, here, we're going to have absolute value of x is x, absolute value of y is minus y. We also have the inequalities that y is less than or equal to y, and minus x is less than or equal to absolute value of x. Okay, so these are very believable if you draw pictures. Now, if x plus y is greater than or equal to 0, absolute value of x plus y equals x plus y. That's less than or equal to absolute value of x plus absolute value of y. Since we have that x is equal to the absolute value of x, we have that y is less than or equal to absolute value of y. So it holds in this case. If we have that x plus y is less than or equal to 0, same idea. We take the absolute value of x plus y, that's equal to minus x plus y. And then we have that's equal to minus x plus minus y, which is less than or equal to absolute value of x plus absolute value of y. So we get the triangle inequality in this case. So that finishes off our proof. Now, I'll leave it to you to figure out how to remove all the cases by adapting argument for case 3. For our final method of proof, we have mathematical induction. Now, induction is only going to apply to certain types of theorems. For these, we'll want to prove a collection of statements, P of n, where n ranges over the positive integers. Then our procedure is, first we're going to prove P of 1. We'll call this the base case. Then we're going to want to show, okay, assuming that P of k is true, we want to prove that P of k plus 1 is true. So this is what we call the induction step. So what's happening here, this is like trying to climb a ladder. If I want to climb a ladder, I need two things. First, I need to know how to get on the ladder. It's going to be our base case. Then I need to tell you how to go from one rung to the next rung. So that's what's happening in our induction step. So I get on the ladder, then I can climb up one rung at a time. One thing to note about the base case, okay, it won't always need to be P of 1. It's just going to have to be P at some definite starting point. Now, let's take a look at an example. Our theorem is, okay, I want to prove using induction for n greater than or equal to 1, n times n plus 1 is even. Now, we don't need induction to prove this. Okay, you'll note if I have any two consecutive integers, okay, if the first one's even, the next one's odd, we take the product, we get an even. If the first one's odd, the next one's even, we take the product, we get another even. We just want to use a simple example for our first induction proof. Now, okay, our collection of statements, we have P of n, n times n plus 1 is even. For my base case, we have P of 1, So that's going to be 1 times 1 plus 1 is even. So that's the same as saying 2 is even. And we know that's true. For the induction step, we're going to assume P of k is true. Okay, and this is also called the induction hypothesis. I want to show that P of k plus 1 is true, assuming this. So we usually have to go and do some work off to the side, and then we come back and write the proof up nicely. With induction proofs, one good way to do your work is to start on one end, go to where you want to wind up, and work your way to the middle. We'll see some more examples of that. Now, to start, I'm going to write out P of k plus 1. So I know I'm going to start with k plus 1 times k plus 2, and we want to show that this is even. So we just follow this out. So we multiply, I get k squared plus 3k plus 2. Then I need to figure out how to get our induction hypothesis into our argument. Now we note what we're assuming to be true is that k squared plus k times k plus 1 is even. So I'm going to take a k squared plus k out of this. That gives me k squared plus k plus 2k plus 2. Now, because we're assuming that k squared plus k is even, that means we could write that as 2 times j for some integer j. So I'll have 2j plus 2k plus 2. I could factor a 2 out of this, and I get 2 times j plus k plus 1. I have 2 times an integer, so that means our original number is an even number. That means our induction step is true. So that means our proof by induction holds. So our theorem is true. Let's look at a bad induction proof. Our theorem, all marbles are blue. I want to break this out into a sequence of statements for which induction applies. Okay, we have P of n. Every set of n marbles consists of blue marbles. For a proof by induction, okay, I'm going to assume P of k is true, and we'll use that to show that P of k plus 1 is true. Now, we have a collection of k plus 1 marbles, so I'm going to remove one, put it off to the side. That leaves a collection of k marbles. By the induction hypothesis, they're all blue. Now, we'll take our original marble, put it back in the set, then remove a different one. Again, I have a collection of k marbles, which are all blue now. So our original marble was also blue. We take the second marble and put it back. We have a collection of k plus 1 blue marbles. So that shows our induction step. Now, this statement's clearly false, so what's going wrong? Well, we didn't show a base case, and we note, okay, if I want every set of one marble to consist of blue marbles, that's going to be false. So we know that there exists out there somewhere a brown marble, so this is not going to hold. It's also worth noting, if you check the argument, it'll fail when n is equal to 2. As a final note, we point out technique of complete induction. So for this technique, okay, we can prove that this works using induction itself. What this says, instead of just assuming in your induction hypothesis that P of k is true, you can instead assume that P of I is true for all I between 1 and k. So instead of just assuming P of k, we can assume all statements leading up to k and including k. Now this is going to be useful for when, instead of just assuming one statement for the induction hypothesis, P of k, you may need P of k minus 1, P of k minus 2, or whatever number of statements besides the one of interest.